So I think we can get started. So it's a real pleasure to open the GGI symposium with Yonit Hochberg from the University of Jerusalem, and she's going to talk. Before starting, just a quick note for the people in the room. If you want to ask a question, please wait until the microphone gets to you, because otherwise the people on Zoom will not hear anything. I know it's tedious, but it's inevitable. So thank you very much, Yonit, for accepting to speak, and the floor is all yours.
Not really.
Yeah, I can hear you guys now.
Ah, okay, good. So it's just a matter of shouting.
Okay, so I let you shout
you let me
that
shout.
We can start. Yes.
Okay, I think we can start. So today is the first day of the symposium, and we are very happy of having like a day dedicated to dark matter and dark matter searches over all the dark matter scales. So we start with Yonit Hochberg from Jerusalem University, talking us about light dark matter. You can go, Yonit.
Okay, thanks so much. Thanks so much to the organizers for inviting me. And hi, everyone. I'm really jealous of those of you who are sitting right now in the GGI lecture hall. I really wish I could be there, and hopefully it won't be another year until the next GGI before I'm back to traveling around the globe. So it's really nice to see you guys virtually. And I'm going to be talking about a topic that, if you've spoken to me over the last few years, it's no secret that I'm super excited about, and that's light dark matter. So let's start at the beginning. I think it's no secret to this audience that the star of the show for the past 40 years in the context of dark matter has been the WIMP, the glorious WIMP, with, of course, appropriately stated caveat about axions. And the idea is extremely simple, right? And we're all familiar with this. Dark matter particle that undergoes 2-to-2 annihilations in the early universe, then we can have a relic abundance left over. And if we just parameterize this thermally averaged cross-section by some coupling squared over mass squared, then we find there's a particular size for this cross-section, or a particular relationship between mass and coupling, such that we get the right relic abundance. And that tells us that the mass of dark matter should be the coupling times around 30 TeV. And so it happens to be the case that if this coupling is of order an electroweak coupling, then the weak scale emerges. So this is the weakly interacting massive particle, or the WIMP miracle. And this has really been our dominant notion for dark matter for nearly 4 decades. And it's really easy to understand why, because it's extremely simple and it's extremely predictive. And as this has been our dominant notion, it's also been guiding our experimental searches. And at all experimental frontiers, whether it's at the lab when we look at direct production, or deep in the lab underground where we look through direct detection, or even up in the sky where we look for indirect detection signals, our experiments are getting increasingly sensitive, and yet we haven't detected this dark matter. And so I view this moment in time as a really incredible opportunity for new ideas to emerge. Because if you think of it, that WIMP mass range really spans just a small fraction out of a vast parameter space in which dark matter can reside. And this is really, I think, the theme for this opening symposium session. So Eric is going to be talking about sort of going to the heavy side of dark matter. Jungwoo is going to be talking about going super, super light. And what I want to focus on in my time with you is on what I'll call light dark matter, which is really going between, let's say, 3 to 6 to even 12 orders of magnitude lower in dark matter mass. And I think that this window of masses really opens up a new frontier for dark matter physics. And it's a field that's seen a lot of activity in recent times, both from the theory side and the experimental side. And so I hope to give you a little bit of a sense of how these two theory and experiment fronts have been making progress together. So let's start with theory. So new theory ideas that give us light dark matter are actually extremely abundant. So I put together to show you how easy. So here's my first example. It's exactly the WIMP. Okay, so let's look at the exact same process, 2-to-2 annihilations of dark matter. The cross-section is parameterized in the exact same way, and our dark matter mass and coupling relationship is likewise identical, except now instead of taking a coupling that's of order the electroweak coupling, we can just take a coupling that's substantially smaller. Okay, and then we naturally get dark matter that's lighter than the weak scale. My second example are forbidden channels. So again, we can look at the exact same process of 2 to 2 annihilations, but now we can consider a kinematical regime where the sum of incoming masses is smaller than the sum of outgoing masses. Right, so at 0 temperature, this process, of course, would be forbidden. But importantly, our early universe is a thermal environment. And so in the early universe, this process
Yonit,
can... Yeah.
Sorry to interrupt you. Can you turn off your video, like your camera? Because it seems that you're, I mean, sometimes you are breaking up a bit.
Okay, sorry about that. So the second example are forbidden channels, where I can still look at the exact same type of process of 2 to 2 annihilations, except now I look at a kinematical regime where the sum of incoming masses is smaller than the sum of outgoing masses. So at 0 temperature, this process, of course, would be forbidden, but our early universe is a thermal environment. And so this process can happen in the early universe through living off of the Boltzmann tail of the distributions. And so if we look at the relationship between mass and coupling to get the right relic abundance, the relationship is exactly like it was for the WIMP, except now we have this additional exponential suppression factor coming in from that Boltzmann suppression. And so in this case, we actually get dark matter that is exponentially lighter than the Lee scale. Third example, SIMPS, what's speaks. In this case, the first process that can control the relic abundance of dark matter by changing the number density are 3 to 2 self-annihilations of dark matter. And so if you just parameterize this kind of weird object of a 3 to 2 cross-section as some coupling cubed over mass of dark matter to the 5th, and in terms of dimensions, this is correct, then now if you solve for the relic abundance, you find a very different relationship between the mass and the coupling. You find that the mass should go like the coupling times around 100 MeV. And so now it happens to be the case that if this coupling is a strong coupling of order 1, then the strong scale emerges. So instead of a weakly interacting massive particle, we now have a strongly interacting massive particle, or instead of a WIMP, we now have a SIMP. So SIMPs are dark matter candidates with strong self-interactions, typically with mass between the MeV and the GeV scales. So I've given you a few examples from the theory side of how it can easily get light dark matter. And now I want to move to talk about experimental ideas. So here's, we have many different experiments that are searching for dark matter in the laboratory. And although they all differ in some ways, they all roughly follow the same detection blueprints. Okay, so the idea is that we have some target that's sitting in a lab, typically deep underground. And we hope that dark matter is going to come in. It's going to interact with that target. There's going to be some reaction of the system, and we want to measure that reaction. Okay, so dark matter comes in. It hits the target gets excited. Maybe it's going to emit electrons or photons or phonons. Something is going to happen, and we're going to measure what that something is. And so here's a plot that you've probably seen many times from that direct detection experiments show us. The constraints that they can place on the interaction cross-section between dark matter and nuclei as a function of dark matter. And common to all these experiments that are indicated by the colored curves in this plot is that they typically a big dark matter that's coming in. If I'm a big ball, I'm trying to punch a big ball that's sitting in the lab, and it makes perfect sense. I'm going to be able to kick this heavy nuclei. But what happens if dark matter is substantially lighter? Then my interaction is more like a tiny little ping pong ball that's trying to give a kick to a big bowling ball. Okay, it's just not going to work. That light dark matter can't give a big enough punch to kick the heavy nuclei. And this is why these experiments are losing sensitivity when the mass of the dark matter drops beneath the GeV scale. And so if we want to be sensitive to light dark matter, it's much smarter to scatter off of something lighter, such as electrons, where the kinematics is more well matched. And this fundamental understanding really sits at the basis of all of the different proposals that have been proposed recently in the literature. And to understand those, let's walk through the following energy guideline. So if I want to think of dark matter that is scattering with electrons, then the maximum energy that I could possibly deposit into the system is the entire kinetic energy that the particle is carrying, right? So kinetic energy is mass times velocity squared. Since velocity is of order 10 to the minus 3, I have the maximum deposit that's a factor of 10 to the minus 6 times the mass. And so that means that if I want to be sensitive to GeV masses, I need systems that are sensitive to KV energy deposits. Similarly, if I want to go down to by 3 orders of magnitude to the MeV scale, then I need systems that are sensitive to very small energy deposits of order an eV. And if I want to be really greedy, and I'll go all the way down to the warm dark matter limit of a keV, then I need systems that are sensitive to really tiny energy deposits of order milli-electron volt. And we can organize all of the existing ideas in the literature based on the size of that energy deposit that they're sensitive to. And so I wrote down many of those ideas over here, and you see some of them use interactions with electrons, as we discussed. Some of them even use interactions with nuclei in smart ways, primarily by using phonon interactions. But there's really been just an explosion of interest and ideas in recent times. And what I'd like to do is just walk you again through a few of these ideas to give you a sense of the type of targets, the type of detection methods, and the type of philosophies that people have been talking about to sort of open your mind to this direction. So let's start with the first example, which are really the first ideas that were put out around a decade ago, where it was proposed that maybe dark matter could come in and deposit enough energy to ionize an atom. Or maybe dark matter would come in and deposit enough energy to excite an electron in a semiconductor from the valence band up to the conduction band. And so in terms of the energies for ionizing, let's say, a typical atom like xenon of order 10 eV of energy is needed. And likewise in semiconductors, whether it's germanium or silicon, and recently we've been able to show that even diamond and silicon carbide can be excellent targets for this, the energy of that gap to excite the electron is of order an eV. And so based on that energy guideline that we discussed, this tells us that we should be sensitive, or could in principle be sensitive, to the MeV scale of dark matter masses in these systems. And these theoretical ideas are actually being experimentally realized these days. And so from the atomic ionization side, xenon 10, 100, 1 ton, et cetera, are really leading the charge. And from the semiconductor side, Super CDMS and Sensei with very different and distinct silicon devices have already started placing strong limits on this light dark matter parameter space, pushing down towards the MeV scale. But what happens if we want to go to even smaller masses? Okay, this is something that we fundamentally can't do through electronic excitations in these systems because of the energies that are involved. And so for smaller masses, in come example number 2, which are superconductors. So in superconductors, the ground state of the system is no longer free electrons, but it's energetically favorable for these electrons to follow the buddy system. And so they pair up in pairs that are called Cooper pairs. And in these systems, the binding energy of these Cooper pairs, which is the same as the gap of the system, is indeed of order milli-eV. And so these systems could in principle be sensitive, based on that energy guideline, to dark matter masses all the way down at the keV scale. So the idea is that dark matter would come in, deposit enough energy to interact with these Cooper pairs, deposit enough energy to break those Cooper pairs apart. That creates some excitations in the system that we can somehow detect. And in our original proposal a few years back, we had proposed to use a philosophy that's very similar to what Super CDMS does in their silicon devices, which is using an excitation concentration philosophy. But what I'm going to mention here today is a more modern, a more recent approach that we've put forward, where we use the sensor plus target philosophy. So for this, our technology of choice that we've explored is a very mature technology that's originally been developed for a completely different field of research, for quantum information science. So these are very long names: superconducting nanowire single photon detectors, or in short, they're called SNSPDs. And these is a very mature technology. And the idea is that you take this little nanowire, and dark matter will come in. It's going to ram an electron in this nanowire. That's going to create some hotspot, which will cause the electrons to diffuse away. And that creates a resistive region across the nanowire, which results in a voltage pulse that we can read out. And essentially what we propose is to apply this technology for the first time towards the dark matter hunt. And so we propose to use these nanowires simultaneously as the target with which dark matter is interacting, as well as the sensitive sensor that realizes that this interaction had occurred. And of course, in order to one day build up en masse, we would hope to multiplex these. And we already have an existing prototype device that's already giving us science results that really serves as a proof of concept for this idea. And I'll be showing you those results in a few minutes. But what about directional information? So in the original idea of how, for instance, Super CDMS looks in semiconductors, or in our proposal for bulk superconductors, if what we're doing is detecting secondary excitations, then in principle, there's a lot of potential to lose any directional information. We're starting to explore in recent work the possibility to actually hold on to some of that directional information in superconductors. But what I want to talk about now is the idea that if we can observe a primary particle that we've interacted with, that primary electron, we have a lot of hope of retaining directional information. Okay, so this is something that we can hope to do in two-dimensional targets. And so I'll tell you in particular the story for graphene, but keep in mind that you could actually do something very similar also with these nanowires as well. So graphene is a two-dimensional target that has a vanishing or nearly vanishing band gap, but we actually don't have to use any of the beautiful properties of graphene. The only thing that we care about is that in order to eject an electron in this material, we have to overcome the work function, which is of order a few eV. Okay, and so if I deposit a few eV of energy into graphene, I can eject an electron. And that means that in principle, through the energy guideline we discussed, I can hope to have sensitivity to MeV scale dark matter masses. So the idea is that dark matter would come in, it's going to scatter with these valence electrons, deposit enough energy to eject them from the material, and we're going to detect that ejected electron. So this is an eject and detect philosophy. And the real strength of this proposal comes from the fact that if you track the direction of that ejected electron, then it turns out that it's actually a good tracer for the direction of the incoming dark matter. Okay, and so that means that we're naturally going to have forward-backward discrimination power or directional signal in this type of setup. You know, so imagine at a certain point of the day, my dark matter wind is coming in exactly from the bottom of these graphene planes, and the electron is ejected into the vacuum over here and detected. But now, fast forward to 12 hours later, as Earth has rotated around its axis, now the relative direction of the dark matter wind is exactly reversed, and it's coming in from the top, and that ejected electron is now going into the substrate. And so the electron is not detected or detected as something different. So we naturally have a way over here to separate signal from background. And you might think that it sounds crazy to ever be able to hope to mass up a large amount of graphene until you find out that there's an experiment that plans to do exactly this. So there's an experiment called PTOLEMY, which was originally proposed to detect relic neutrino through their capture on tritium. And it turns out that they intend to use around 0.5 kilogram of graphene on which they're going to lay their tritium. And so we essentially propose to borrow their bare graphene sheets before they load it to run it as a dark matter experiment. And this idea has been officially adopted by the PTOLEMY collaboration, which, as you see from this title I stole from the archive, is now officially also a proposal for a directional detection of MeV scale dark matter. And it's a lot of fun. It's a lot of fun as a theorist to be getting to see a little bit about how an experiment works from the inside. So I've given you a whole bunch of ideas of different materials, and anytime somebody tells you a material that they want to use as a dark matter target, you of course have to go ahead and compute some rate. What's my event rate? And of course, different factors that come in here. You care about the target density, and there's a piece that cares about the dark matter flux. You care, of course, about target properties. This is where very often condensed matter physics and material science comes in. And the particle physics, of course, sits in that cross-section of the interaction. And so here's a plot of potential reach of these types of ideas that we put together in a community report a few years ago. And it shows you on the x-axis is, of course, dark matter mass, now in units of MeV. And the y-axis is interaction cross-section with electrons. In this particular case, it's via a light mediator, and it's a reference cross-section with a particular reference momentum, as is conventional in the field. And what you see are all of these different colored curves are showing you the different projected reach for different materials. So let's just look at this whole bunch that are cutting off over here at the MeV scale. These are all the different ideas that have roughly EV energy deposit sensitivities. And out of those, let me just point out this dashed green, that's the graphene proposal, okay? And so you see compared to others in the same energy regime, it does better than some, worse than others. But importantly, out of all of them, it is the only one that has the potential for directionality, which would be so important were we to see a signal, since this would be able to allow us to really say that what we're seeing is dark matter. And this dotted green curve down here shows you the projected reach for superconducting targets, which you see if we could construct would really just be completely amazing. And to show you that this isn't science fiction, as I mentioned, we have a tiny little prototype device made of tungsten silicide. It's really tiny. It's just around 4 nanograms of material. We know it had 0.8 eV of threshold. And at the time that we published our first PRL on the topic, we had observed it for 10,000 seconds. That's around 3 hours and seen no dark counts. By now, we actually have substantially more data. And so here's our updated limits that we were able to place, again, just from looking for a few hours at this tiny little device. So you see over here, again, cross-section as a function of dark matter mass. The shaded blue is the bound that we're able to place with this tiny little device. And these solid colored curves are showing you as we would hope to go to larger arrays of nanowires while pushing thresholds lower and keeping dark counts low, we could really hope to have incredible reach into light-dark matter parameter space. There's a lot of uncertainty in these curves, and in particular, the fact that our device is not a bulk device, but rather there are some geometric effects, which we're just starting to explore, which could even potentially enhance the reach further. And importantly, I'm not trying to advocate for any particular technology or design, but really just to outline how through improvement to moderate improvement to existing technology, we could really hope to have incredible reach into light-dark matter parameter space. And indeed, we're nowhere near the fundamental limits on the thresholds of these devices. So my experimental collaborators have recently, just a few months ago, have demonstrated in a similar nanowire sensitivity to 10 micron wavelength. So in particle physics units, this corresponds to 125 millieV energy thresholds. And in fact, it's even possible that the nanowire that we use to place limits is actually sensitive to lower energies as well. And so this really just goes to show how, as we push to lower thresholds while building up in arrays, an array size, we really can hopefully do a lot more than is currently being done. And in the process, we've also been able to develop a new formalism for how to compute these scattering rates. And that's because it turns out that the way that dark matter interacts with electrons in any material is completely determined by a measurable quantity, the dielectric function of the material, or the loss function. And this is true for any dark matter interaction that couples to electron density, whether it's a scalar or a vector. And the reason that this is so important is that historically, the way that rates have been computed is by using single particle excitations. But this formalism automatically includes all of the many-body effects of the material. So any collective modes, such as plasmons, can really come in, and we can really understand the full reach of these materials. And we can also understand and identify optimal properties of materials that will help us build, hopefully, optimal dark matter detectors. And just to give you one example, through using this formalism, we were able to identify just a particular material called heavy fermion of a heavy fermion system, which is indicated over here in green, just because of particular features that it has in this measurable quantity in its loss function. And so I really think that we're far away from identifying, have reached the optimal materials. And there's a lot of hope for us to now really be able to design materials to be optimal for the light-dark matter search. So in short, I hope I've convinced you that light-dark matter is a very active field of research. This is true both from the theory side and the experimental side. And importantly, I think that these ideas are by no means exhausted. And if there's one thing that I've learned in my last few years working on this topic, is that it's totally fine for an idea to seem crazy at first, because it might just be that your crazy theory idea turns out to be completely generic in theory land, or that your total crazy experimental idea, maybe there's an experimental colleague from a different field who just happens to have a device lying around in their laboratory that they never thought to apply for dark matter, and you could be placing the strongest limits using that. And so I really think that the best ideas might be ahead. And for me personally, I find it really inspiring that if I think of where we were as a community just around a decade ago, we had all of these incredible ideas for how to search for the WIMPs, and those are going to continue to push forward in upcoming years. But if we asked what did we have for light dark matter, we really didn't have much. And just looking at this incredible amount of activity that's been going on in the last few years is really inspiring to me. And importantly, even though we're theorists that are sometimes coming up with these ideas, the work is really being done in close contact with experimentalists who really have the power to bring this into fruition. And this isn't just experimentalists within the particle physics community, but this work really sits at the interface between particle physics, condensed matter physics, quantum sensing, and precision measurements. And I think the more these communities talk to each other and interact with each other and engage with each other, the better science we're going to be doing. And so I'll just end by saying that if you have any crazy new ideas, you're very welcome to be in touch. And I'll thank you for your time.
Thank you. Thank you very much, Yonit. I don't know if you could hear us clap, what we did.
I heard you just now.
Enthusiasm. Okay.
Okay.
So if you have any questions for Yonit, ask now, because she's probably not going to be able to be here for the discussion, or at least not for all of it.
Yeah, I apologize. I have to go pick up some babies.
Any questions in the room?
Hey, Yonit.
Hey.
And also Mina, I saw it raise her hand. So my question is just about you showed the sensitivity plot before. how does it compare for the sigma E, the interaction with electrons? How does it compare with cosmological limits?
So, so I haven't put on here, sorry, let me just go back to like an example of this, okay? So I haven't folded into here anything that I would view as model dependent. And so, you know, how does one do model building for keV scale dark matter that goes down with these size cross section is, I think, something that's a really interesting theory project. I think there's a big difference in my mind between if there's a no-go theorem about a certain region of parameter space, then I think it's very important to be stating that. But if there's no no-go theorem, I think it's important to also be exploring it, both from understanding how I could detect it, if I have a device that can detect it, and simultaneously in terms of doing model building. So there are different ways that one could play around with cosmological, with the interactions that would enable dark matter to be sitting in this parameter space. I don't think it would be the vanilla 2-to-2 WIMP that's sitting in the keV scale, but that doesn't mean that there's a no-go theorem for it. I think that's the division in my mind.
So, Mina, you can actually unmute yourself and just ask the question.
Okay, thank you. So I have actually the same question that was asked before. I don't know who asked it, by the way. It's about a model that goes down to a keV because you run into trouble with BBN, stellar cooling bounds, so it would be nice to have a model there. The other question I have is about backgrounds. Because you showed a plot where there was, for the superconductors, it was going down to a cross-section of 10 to the minus 52 centimeters squared, if I'm not mistaken, 53. So yeah, so I'd say, so first, I want to point out, so this plot from the community report is several years old. And since that we've been able to understand through this dielectric function formalism to understand that actually in medium effects are actually in place for all dark matter interactions that just care about electron density. And through that, I think then the numbers that you should be looking at are really these updated numbers that are sitting over here. Okay, so this is really the size of the cross section that you should be thinking about. Certainly, when we place bounds, we take into account the actual data, so we understand how many, what the dark count rate was, and so assuming that this is not dark matter, we can at a certain confidence place certain limits. The projections that I show over here are currently projections, of course, for zero background, and this is true for typically true when one proposes a new idea for how you can detect dark matter. You start by, in an ideal situation, can I even do something interesting? And then, of course, you figure out how you can work, what kind of backgrounds you can expect to have and how you can mitigate those. And many of those can be mitigated by, we're not talking about operating these devices sort of in a vacuum of knowledge. Many of the technologies and the methods that are used currently by direct detection experiments can be used to mitigate some of these backgrounds. And I think the real challenge, backgrounds are of course super important, the real challenge is sitting in the unknown backgrounds that you can really understand or try to understand. Once you've understood what's a good, in an ideal situation, a very strong and powerful idea for a detector, and then you sit down and do R&D for that particular design, and then you work out together with experimentalists to compute what are those backgrounds and to understand how you can mitigate them. But that's a step ahead of first identifying in an optimal situation, do these detectors even do something interesting? And that's, I think, the status that these ideas are sitting in. Sorry, but I thought, anyway, I just think that for those detectors, given that we've done scattering experiments for dark matter, it would have been hard to even estimate the background. Why not give
in the curves that I'm showing here?
Even the original ideas, I'm making a general comment that I'm not of the opinion that we should put out ideas that just show signal contours. They should have some background estimates, given that the physics we kind of know in this mass range, right?
I don't think that that's 100% accurate, because depending on how you build on the particular design of an experiment, I might be able to mitigate some backgrounds, and there are other backgrounds that I won't be able to know. So, for instance, in the paper that I alluded to when we're talking about directionality for superconductors,
we're able to show that, for instance, a curve of this sort that's shown over here for this, let's say, kilogram year exposure, okay, of 10 millieV threshold of an aluminum, even bulk superconductor, with the directionality that we now understand through the how down conversion happens in the material. Okay, so if I have directionality, that's a very clean way for me to be able to separate signal from background. You lose a factor of maybe a factor of 10 in your reach. So that's an example of how even looking at a zero background, will be actually very, very informative. And as you said, perhaps there's a comment that you feel about many of the papers in the field, but to be able to compare apples to apples, understanding first in the zero background limit, what is the reach, is really the first step to understanding which experiments we should convince experimentalists to go after. And certainly one can fold in expected backgrounds to understand what an actual experiment would reach.
Thank you.
I also have a question, Yonit. So what change, I mean, in this new projection that you show us, basically what you're taking into account are like screening effect in the material. That's why the reach is reduced, or?
Mm-hmm.
Is it correct? Is this correct, or?
Yeah, it's using a more accurate, as I said, I think there's still, we still have a way to go for these thin devices to understand their reach. There's very likely a substantial enhancement that this reach gets through accurately taking into account the geometry of the device. Because the fact that you can in principle have energy that's deposited in other regions of the device that can be dissipated gives you actually effectively a volume enhancement. So, you know, these tiny little super thin nanowires, for instance, are sitting on much, much thicker layers of other materials. And effectively, you can also get actually a volume enhancement from that. We're in the process of my experimental colleagues are in the process of validating that and characterizing that response so that we can fold it into these projections. But yeah, the big difference in the superconductor reach that I'm showing here compared to the one that we had several years ago in that community report is now an accurate understanding of the proper formalism for how to account for in-medium effects, and understanding that actually, as long as all you have is just a weak probe, then all you're really probing is the material response. And so that's a measurable quantity that you can take into account. Yeah.
So the other thing is like regarding cosmology, just a comment. Are you thinking about subfraction of the dark matter that would avoid problem with CMB? Like
not necessarily. I mean, not necessarily. I think I do want to separate here between.
Because, I mean, the cross section is just the same, right? I mean, this is 1-to-1. I mean, there is no model building. I mean, unless you are thinking about.
Not necessarily, because it doesn't have to be 2-to-2 annihilations, for instance, that control the relic abundance.
No, but it's just a scattering. What Fear was referring to is just dark matter scattering with electrons that would modify, just would scramble the peaks of CMB.
Yeah, so I think what's important to me is I really, in my mind, this is at least how I operate. I keep two things separate when I'm trying to think of what can be done. And that's what can I do with model building? What can I do from the theory side? And as I said, I work on that and I'm very interested in that as well. And I think to do the model building for sub-MeV is still, for sub-MeV candidates, is still like between the KV to MeV range is very much still in its infancy. I do not see a no-go theorem for how I can't avoid. And so in the absence of that no-go theorem, I think it's A, important to be building those models and constructing those theories, and B, to be trying to understand how we can detect whatever we can detect with existing technology or pushing technology to its maximum. That's my philosophy.
Okay, thanks.
I have a question. Where is the new?
Sorry?
In these plots?
Sorry, can you say that again, please?
Where would the neutrino flow be in these plots? Say from coherent scattering with the nucleus of the whatever target you're choosing, and that ionizes the medium, so to say, and kicks out some electrons?
Yeah, so what I can tell you, we've actually, in our first superconducting paper, we had actually computed this. And so because of how, even if you assume, let's say, because of how the spectrum looks at these low energies,
then if you go to, if you, let's say, look at deposits between milli-eV and an EV, so typically an experiment will have a dynamical range of, say, 3 orders of magnitude, you would have less than 1 event in a kilogram year. And if you look at the 10 milli-eV up to going 3 orders of magnitude up to 10 EV, then you'd have, you would have, I think it was 3 events. And so you can fold this in, it gives you a slight shift into your curve. But essentially at these energies, in a kilogram year, you don't have, you really don't see much of this affecting your reach. We're far away from, this is a very different situation than we are already for the WIMP, which has been running for 40 years, where we're starting to really, build these tremendous experiments that are pushing closer and closer. The background behaves different, and we're very far away from touching anything related to that floor.
Okay, thanks.
Hi, Yonit. I have a similar question regarding the backgrounds, but I'm just going to phrase it differently. So there's an experiment that's called lamppost that probably you know well. They also had superconducting nanowires as the detectors, and they had a very small exposure, and they did see backgrounds. That's my understanding. They observed a few events per nanogram day or something. So my question is, if you scale up their backgrounds to the kilogram year exposure that you have here, how many events will you have in that kilogram year?
Yeah. So that's a great point. So let me also clarify this bound that we placed here is exactly using the data on the nanowire from the lamppost work. Okay, so the experimentalists, there's a subgroup of the experimentalists who are working on the lamppost paper who are the co-authors of these nanowire papers with me.
Right.
And so this is exactly taking into account those 4 dark count events of one of the 2 nanowires in that lamppost experiment. I think we probably even put together projections for one of the proposed, experimental proposals for funding that we put through, which even would have those curves. But I think there's a very big difference between, and we can try to do that exercise. And then of course you have to scale up this curve if you were just going by area. But that experiment has not been, those nanowires, I should say, the nanowires have not been designed right now in order to optimize the reach, both in terms of keeping dark counts as low as you can go, while having thresholds as low as you can go as well, and building up in mass. And these are different features that, of course, some of the geometry of the device can come into play, some of the materials, the width, many of the features of how they construct these devices can come into play. These devices haven't been designed for that right now for that particular purpose. And so I think we can do the exercise of doing this scaling, but you're not going to get something that's going to be indicative of what the true reach would be if you were to build up in mass, because I think we can, and I say this because the experimentalists would say this too, we can do much better than just that naive scaling.
But how do they know that? Because the origin of those backgrounds, I thought they were not known. So how are they that sure that once you scale up, the backgrounds won't scale up with exposure? I mean, I understand that people mitigate backgrounds by 2 or 3 orders of magnitude. That I can understand. But going from nanogram, they had nanogram day or something like that, right? I don't remember their exposure, but to kilogram year, that seems like that they will need to mitigate whatever background
so the
now
kilogram,
by a million.
Okay, yeah. The kilogram year, you can think of also as it could be using the original idea of using bulk superconductors, for instance. And in the bulk superconductors, we believe that we should be able to extract directionality at these very low energy deposits. And if that's true, then certainly no naive scaling just by multiplying of the backgrounds would give you the accurate estimated reach even. Okay. So I'm not saying that there isn't a scale up. I'm saying that just taking that naive scale up, does not give you the accurate reach.
Okay, thank you very much to both of you, especially for the work. So, Yonit again. Now, unfortunately, we have to move on.